네, 안녕하세요. 오늘 14강 동영상 강의로 하겠습니다. 14강 partial differential equation 추가로 나가도록 할게요. 저번 시간에 이어서 PDE 중 대표적인 이퀘이션, 히트 이퀘이션에 대해서 조금 말씀을 드리겠습니다. 히트 이퀘이션은 디퓨전 이퀘이션 중 하나고, 디퓨전 이퀘이션은 이런 꼴로 이루어져 있죠. 시간에 대해서 한 번 미분, 공간에 대해서 두 번 미분한 이런 꼴로 돼 있어서 이 내가 알고자 하는 이 목적 함수가 concentration일 때는 diffusion equation이라고 얘기하고, U일 때는 유속일 때는 momentum equation, 그 다음에 T일 때는 thermal diffusion equation, 뭐 이렇게 heat equation이라고 하죠. 이렇게 표현을 하고, 얘에 대한 솔루션을 푸는 거는 separating variable로 풀면 됩니다. 그래서 우리가 프리에 시리즈가 나오는 건 당연하고요. 그래서 우리가 1D 히트 이퀘이션을 한번 보게 되면 바운더리 컨디션이 이렇게 주어집니다. 바운더리 컨디션이 이렇게 주어지고, 이니셜 컨디션이 이렇게 주어져요. 그러니까 t가 0일 때 어떤 ux에 대한 함수가 fx로 표현이 된다 라고 볼 수가 있죠. 그래서 스텝 1, 2, 3 요거는 저번 시간에 배운 separating variable랑 동일한 방법으로 우리가 풀 수가 있어요. 그래서 두 가지 식이 나오는 거죠. 시간에 대해서 식과 공간에 대한 식, 이렇게 두 개를 갖고서 바운더리 컨디션을 우리가 써서 아이젠 펑션 구하고, 그걸 프리 시리즈로 구하는 방식입니다. 그래서 히트 이퀘이션에 대한 서플리먼털 비디오를 하나 좀 볼 텐데요. 이걸 같이 한번 시청해 보도록 하겠습니다.
We last left off studying the heat equation in the one-dimensional case of a rod. The question is how the temperature distribution along such a rod will tend to change over time. And this gave us a nice first example for a partial differential equation. It told us that the rate at which the temperature at a given point changes over time depends on the second derivative of that temperature at that point with respect to space. Where there's curvature in space, there's change in time. Here, we're going to look at how to solve that equation. And actually, it's a little misleading to refer to all of this as solving an equation. The PDE itself only describes one out of three constraints that our temperature function must satisfy if it's going to accurately describe heat flow. It must also satisfy certain boundary conditions, which is something we'll talk about momentarily, and a certain initial condition. That is, you don't get to choose how it looks at time t equals 0. That's part of the problem statement. These added constraints are really where all of the challenge actually lies. There is a vast ocean of functions solving the PDE, in the sense that when you take their partial derivatives, the thing is going to be equal. And a sizable subset of that ocean satisfies the right boundary conditions. When Joseph Fourier solved this problem in 1822, his key contribution was to gain control of this ocean, turning all of the right knobs and dials so as to be able to select from it the particular solution fitting a given initial condition. We can think of his solution as being broken down into three fundamental observations. Number one, certain sine waves offer a really simple solution to this equation. Number two, if you know multiple solutions, the sum of these functions is also a solution. And number three, most surprisingly, any function can be expressed as a sum of sine waves. Well, a pedantic mathematician might point out that there are some pathological exceptions, certain weird functions where this isn't true. But basically any distribution that you would come across in practice, including discontinuous ones, can be written as a sum of sine waves, potentially infinitely many. And if you've ever heard of Fourier series, you've at least heard of this last idea. And if so, maybe you've wondered, why on earth would anyone care about breaking down a function as a sum of sine waves? Well, in many applications, sine waves are nicer to deal with than anything else, and differential equations offers us a really nice context where you can see how that plays out. For our heat equation, when you write a function as a sum of these waves, the relatively clean second derivatives makes it easy to solve the heat equation for each one of them. And, as you'll see, a sum of solutions to this equation gives us another solution, and so in turn that will give us a recipe for solving the heat equation for any complicated distribution as an initial state. Here, let's dig into that first step. Why exactly would sine waves play nicely with the heat equation? To avoid messy constants, let's start simple and say that the temperature function at time t equals 0 is simply sine of x, where x describes the point on the rod. Yes, the idea of a rod's temperature just happening to look like sine of x, varying around whatever temperature our conventions arbitrarily label as 0, is clearly absurd. But in math, you should always be happy to play with examples that are idealized, potentially well beyond the point of being realistic, because they can offer a good first step in the direction of something more general, and hence more realistic. The right-hand side of this heat equation asks about the second derivative of our function, how much our temperature distribution curves as you move along space. The derivative of sine of x is cosine of x, whose derivative in turn is negative sine of x. The amount the wave curves is, in a sense, equal and opposite to its height at each point. So at least at the time t equals 0, this has the peculiar effect that each point changes its temperature at a rate proportional to the temperature of the point itself, with the same proportionality constant across all points. So after some tiny time step, everything scales down by the same factor. And after that, it's still the same sine curve shape, just scaled down a bit, so the same logic applies, and the next time step would scale it down uniformly again. And this applies just as well in the limit, as the size of these time steps approaches 0. So unlike other temperature distributions, sine waves are peculiar in that they'll get scaled down uniformly, looking like some constant times sine of x for all times t. Now when you see that the rate at which some value changes is proportional to that value itself, your mind should burn with the thought of an exponential. And if it's not, or if you're a little rusty on the idea of taking derivatives of exponentials, or what makes the number e special, I'd recommend you take a look at this video. The upshot is that the derivative of e to some constant times t is equal to that constant times itself. If the rate at which your investment grows, for example, is always, say, 0.05 times the total value, then its value over time is going to look like e to the 0.05 times t times whatever the initial investment was. If the rate at which the count of carbon-14 atoms in an old bone changes is always equal to some negative constant times that count itself, then over time that number will look approximately like e to that negative constant times t times whatever the initial count was. So when you look at our heat equation, and you know that for a sine wave, the right-hand side is going to be negative alpha times the temperature function itself, hopefully it wouldn't be too surprising to propose that the solution is to scale down by a factor of e to the negative alpha t. Here, go ahead and check the partial derivatives. The proposed function of x and t is sine of x times e to the negative alpha t. Taking the second partial derivative with respect to x, that e to the negative alpha t term looks like a constant. It doesn't have any x in it. So it just comes along for the ride, as if it was any other constant, like 2. And the first derivative with respect to x is cosine of x times e to the negative alpha t. Likewise, the second partial derivative with respect to x becomes negative sine of x times e to the negative alpha t. And on the flip side, if you look at the partial derivative with respect to t, that sine of x term now looks like a constant, since it doesn't have a t in it. So we get negative alpha times e to the negative alpha t times sine of x. So indeed, this function does make the partial differential equation true. And oh, if it was only that simple. This narrative flow could be so nice. We would just beeline directly to the delicious Fourier series conclusion. Sadly, nature is not so nice, knocking us off onto an annoying but highly necessary detour. Here's the thing. Even if nature were to somehow produce a temperature distribution on this rod, which looks like this perfect sine wave, the exponential decay is not actually how it would evolve. Assuming that no heat flows in or out of the rod, here's what that evolution would actually look like. The points on the left are heated up a little at first, and those on the right are cooled down by their neighbors to the interior. In fact, let me give you an even simpler solution to the PDE, which fails to describe actual heat flow. A straight line. That is, the temperature function will be some non-zero constant times x and never change over time. The second partial derivative with respect to x is indeed 0. I mean, there is no curvature. And its partial derivative with respect to time is also 0, since it never changes over time. And yet, if I throw this into the simulator, it does actually change over time, slowly approaching a uniform temperature at the mean value. What's going on here is that the simulation I'm using treats the two boundary points of the rod differently from how it treats all the others, which is a more accurate reflection of what would actually happen in nature. If you'll recall from the last video, the intuition for where that second derivative with respect to x actually came from was rooted in having each point tend towards the average value of its two neighbors on either side. But at the boundary, there is no neighbor to one side, If we went back to thinking of the discrete version, modeling only finitely many points on this rod, you could have each boundary point simply tend towards its one neighbor at a rate proportional to their difference. As we do this for higher and higher resolutions, notice how pretty much immediately after the clock starts, our distribution looks flat at either of those two boundary points. In fact, in the limiting case, as these finer and finer discretized setups approach a continuous curve, the slope of our curve at the boundary will be 0 for all times after the start. One way this is often described is that the slope at any given point is proportional to the rate of heat flow at that point. So if you want to model the restriction that no heat flows into or out of the rod, the slope at either end will be 0. That's somewhat hand-wavy and incomplete, I know, so if you want the fuller details, I've left links and resources in the description. Taking the example of a straight line, whose slope at the boundary points is decidedly not 0, as soon as the clock starts, those boundary values will shift infinitesimally such that the slope there suddenly becomes 0 and remains that way through the remainder of the evolution. In other words, finding a function satisfying the heat equation itself is not enough. It must also satisfy the property that it's flat at each of those endpoints for all times greater than 0. Phrased more precisely, the partial derivative with respect to x of our temperature function at 0t and at Lt must be 0 for all times t greater than 0, where L is the length of the rod. This is an example of a boundary condition, and pretty much any time that you have to solve a partial differential equation in practice, there will also be some boundary condition hanging along for the ride, which demands just as much attention as the PDE itself. All of this may make it feel like we've gotten nowhere, but the function, which is a sine wave in space and an exponential decay in time, actually gets us quite close. We just need to tweak it a little bit so that it's flat at both endpoints. First off, notice that we could just as well use a cosine function instead of a sine. I mean, it's the same wave, it's just shifted in phase by a quarter of the period, which would make it flat at x equals 0, as we want. The second derivative of cosine of x is also -1 times itself. So, for all the same reasons as before, the product, cosine of x times e to the negative alpha t, still satisfies the PDE. To make sure that it also satisfies the boundary condition on that right side, we're going to adjust the frequency of the wave. However, that will affect the second derivative, since higher frequency waves curve more sharply, and lower frequency ones curve more gently. Changing the frequency means introducing some constant, say omega, multiplied by the input of this function. A higher value of omega means the wave oscillates more quickly, since as you increase x, the input to the cosine increases more rapidly. Taking the derivative with respect to x, we still get negative sign, but the chain rule tells us to multiply that omega on the outside. And similarly, the second derivative will still be negative cosine, but now with omega squared. This means that the right-hand side of our equation has now picked up this omega squared term. So to balance things out, on the left-hand side, the exponential decay part should have an additional omega squared term up top. Unpacking what that actually means should feel intuitive. For a temperature function filled with sharper curves, it decays more quickly towards an equilibrium. And evidently, it does this quadratically. For instance, doubling the frequency results in an exponential decay 4 times as fast. If the length of the rod is L, then the lowest frequency, where that rightmost point of the distribution will be flat, is when omega is equal to pi divided by L. You see, that way, as x increases up to the value L, the input of our cosine expression goes up to pi, which is half the period of a cosine wave. Finding all the other frequencies which satisfy this boundary condition is sort of like finding harmonics. You essentially go through all the whole number multiples of this base frequency, pi over L. In fact, even multiplying it by 0 works, since that gives us a constant function, which is indeed a valid solution, boundary condition and all. And with that, we're off the bumpy boundary condition detour and back onto the freeway. Moving forward, we're equipped with an infinite family of functions satisfying both the PDE and the pesky boundary condition. Things are definitely looking more intricate now, but it all stems from the one basic observation that a function which looks like a sine curve in space and an exponential decay in time fits this equation, relating second derivatives in space with first derivatives in time. And of course, your formulas should start to look more intricate. You're solving a genuinely hard problem. This actually makes for a pretty good stopping point, so let's call it an end here, and in the next video, we'll look at how to use this infinite family to construct a more general...
네, 서플 영상을 한번 같이 봤고요. 다음으로는 그 한 예시로 이 삼각형 형태의 이니셜 템퍼레처 이니셜 컨디션을 한번 케이스를 볼게요. 기본 이케이션은 이렇게 1D 이케이션이 이렇게 주어져 있고요. 이때 thermal diffusivity는 conductivity랑 그러니까 density로 아마 표현이 됩니다. 이때 우리가 아이젠 펑션을 이용해서 프리 시리즈를 이용하여 UXT를 이렇게 표현할 수가 있어요. 여기서 이제 주어진 거는 이니셜 컨디션과 프리 인테그랄을 이용한 이제 바운더리 컨디션이 이제 이니셜 컨디션을 이제 구하는 건데 이니셜 컨디션이 이와 같이 이제 주어졌다고 칩시다. 처음에 온도의 어떤 구배가 이런 삼각형 형태로 이루어졌다고 하면 우리는 fx를 현재 알고 있는 거죠. 그렇다는 얘기는 bn의 fx를 바로 넣어서 bn을 프리 코에피션트를 구할 수 있고, 즉 uxt 그러니까 시간에 대한 온도 프로파일을 이와 같은 프리 시리즈로 표현할 수가 있다라는 거죠. 그래서 시간이 0초일 때 이렇게 됐던 애가 0.11로 될 때는 이렇게 뭉툭해지고 점점 얕아지는, 이렇게 감쇄되는 어떤 형태로 간다라는 거죠. 이게 디퓨전 인디케이션의 어떤 성질입니다. 점점 이제 댐핑되면서 감쇄되는 이런 프로파일. 자, 다음으로는 라플라스 이퀘이션에 대해서도 한번 좀 살펴보도록 하겠습니다.
Hello and welcome back to Partial Differential Equations, the video series where we look at some specific PDEs and try to develop a theory for them. And in today's part 2, we start talking about a very important PDE called Laplace's equation. This one occurs a lot in applications, especially in physics when you have something like a potential. However, as always, before we go into the definition, I first want to thank all the nice people who support this channel steady here on YouTube or via other means. And as a reminder, you can use the link in the description to download additional material for the videos. For example, there you can find the PDF versions and quizzes for the videos. And then I would say, let's start with the topic of today by defining the so-called Laplacian. As already mentioned in the last video, this one is denoted by a capital delta and also often called Laplace operator. The term operator fits because it acts on functions and a new function comes out. And here we have a function u defined on Rn or on an open subset omega in Rn. And then the output space is just the real number line as always. And now the Laplace operator acted on u has a nice definition because it just uses the second order partial derivatives of u. More precisely, it uses the 1 with respect to just one variable, for example x1. And then the other ones are just added until we reach xn. So in short, we just have a sum with n terms, where n is the dimension of the input space of u. And in the case you want to write the partial derivatives with the multi-indices, you would say you have d alpha of u, where alpha is always of order 2 with an additional condition. Namely, only one entry alpha j is non-zero. So it has the same meaning as before, we use the second order partial derivatives, but not the mixed ones. And now by using this operator, we can define Laplace's equation as a PDE. And you might already know that it just says that the Laplacian of u should be equal to 0. So we search for the functions u that satisfy this equation on their domain omega. And here I can immediately tell you an application in physics. For example, you want to calculate the electric potential when there is no charge around. So at every point where there is no source, no charge, the electric potential should satisfy Laplace's equation. And in fact, at the end of this video, we can immediately write down some solutions of this PDE. However, first I should tell you that the solutions of this equation have a special name in mathematics. More precisely, we want to have solutions on an open set omega and where the partial derivatives of second order are still continuous functions. So in short, this means we search for a function u in C2. So you know this is the common notation for continuously differentiable functions up to order 2. So obviously for these functions we don't have a problem applying the Laplacian. And in the case we get out 0, we speak of a harmonic function. And you see, it's not hard at all to find examples for harmonic functions, because all the constant functions satisfy Laplace's equation. These are not so interesting, so let's search for some more harmonic functions and maybe the ones with some symmetry. I say that because a radial symmetry allows us to completely solve Laplace's equation. So for the harmonic function u, we can take out the origin from the domain, so we consider it from C2 of Rn without 0. So in the case n is equal to 2, we can simply sketch the whole thing, which means we have the whole space except for one point. So seeing that in the application, you could say that we have a point charge at the origin, and now we want to see what happens outside. And there it's quite natural to assume a radial symmetry, which means that the value of u only depends on the distance to the origin. Hence in our two-dimensional picture here, it means that for a given circle we find the same value for each point on it. And in the formula this would mean that u of x stays the same if you change the direction of x but not the length of x. Which also means that we already get all the values just by looking at one direction. So we can put these values into a real function phi that now only depends on the norm of x. And clearly what we mean here is the standard Euclidean norm in Rn. And obviously this function phi only has to be defined on the real interval from 0 to infinity. And the values are the same as for u, so we land in R. And moreover, a common thing would be to denote the radial variable by R. Hence now everything is just about the function phi of R. So you see, if we already assume that u is harmonic, we need to apply the Laplace operator to this composition of two functions. And then we definitely know the conditions that phi has to satisfy in this case. So again, we assume that u is harmonic, so summing up these partial derivatives gives us 0. Therefore, let's first start with the first order partial derivative del u del xj. There we just have a chain rule because we have this composition of two functions. More precisely, we have phi of the square root of the squares added. So the Euclidean norm in Rn is not so complicated, and we can definitely form the derivative. So the first thing we get here is phi prime of x in the norm, and then times the derivative of the square root times the inner derivative 2xj. So we have 1 over 2 times the square root, which we could write as the Euclidean norm again, times 2xj. So the good thing is we can already cancel the 2, and the whole thing is quite compact. Which helps us because we have to calculate a derivative again. Also not so hard because we just have to calculate with the product rule. So we immediately get here the second derivative of phi. And please don't forget, we also get out the inner derivative again. And multiplying that with the factor we already have gives us the same thing squared. And then finally the product rule tells us that we have a plus now. And there, if you want, you can actually do a quotient rule here for the remaining term. Which means we just have the denominator squared, so the norm of x squared. And in the numerator we multiply this with the derivative of the former numerator, which is just 1. And then we have minus xj times the same inner derivative as before. Hence you immediately see, here it's helpful to multiply with the norm of x in the numerator and the denominator, because then we find the power 3 on the bottom, power 2 here and there. So actually it's quite nice, and now we can form the whole sum, and we already know it's equal to 0. And there you might already recognize the sum here for the first term gives us the norm of x squared in the numerator as well. So this nicely cancels exactly what we want to have. And then for the second part here, we also have the norm of x squared there. However, please note that we have a sum over n terms, which means that this constant term here actually occurs n times. And there we have it. This is what Laplace's equation tells us for the function phi. The second derivative plus the first derivative times n minus 1 divided by the norm of x is equal to 0. In other words, what we get out here is an ordinary differential equation for phi. So let's summarize that as our important result here. A radial symmetric harmonic function u on a pointed domain can be written with a function phi that satisfies this ODE. And we can write this ODE as the second derivative of phi at the point r plus the first derivative of r, which has the factor n-1 divided by r. And this should be equal to 0 for every r between 0 and infinity. So this is quite nice, and with our knowledge of ordinary differential equations, we can immediately solve this one. In fact, it's a linear one which we can solve with an integrating factor. So maybe it's easier to see if you write it as f of r as the first derivative of phi. Because then you just see that we actually just have a first order ODE to solve. And you might remember that the integrating factor just needs the antiderivative of the factor in front of f of r, which is quite simple here because it's just the logarithm function. And since I don't want to confuse, I will use this common ln notation for the natural logarithm. And now the advantage here is that we can use the logarithm rules, which means we can pull in this factor as an exponent. And this is quite helpful because the integrating factor we need to solve the ODE is always given as e to the power of the antiderivative. So in this case, it's simply r to the power n-1. So this is the factor we multiply on both sides, and then we can just use this standard product rule. Hence, the whole differential equation can just be written with one derivative with respect to r. And we use that on the function r to the power n-1 times f of r. And now in this form the ODE is quite easy to solve because we see that the function inside has to be equal to a constant on the interval from 0 to infinity, which then implies that f of r is equal to this constant c1 divided by the function r to the power n-1. And obviously this inverse can also be written as r to the power 1 minus n. And with that we are almost done, because now we only have to integrate this function f of r to get our original function phi. And this already means that we also get in a second constant c2. Moreover, for this integration we also have to distinguish two different cases here. You can see that in the formula of our function, because the case n is equal to 2 gives us the function 1 over r. And there we already know integrating that gives us the natural logarithm function. Hence, in this special case, we have c2 plus c1 times ln of r. And this is the only special case because for a larger n we just have a general formula for the antiderivative. Namely, as you know, we just have to increase the exponent exactly by 1. So we have r to the power 2 minus n with the same factor in front. But honestly, we could push this factor into the constant c1. And there we have it. These are all possible radial symmetric solutions of Laplace's equation on the domain Rn without 0. And often in applications, as already mentioned, the three-dimensional case is important, and you see we just have the function 1 over r here. And soon we will see that this is actually what we call a fundamental solution of our PDE. Therefore I would say, let's continue with that in the next video. So really hope I meet you there again, and have a nice day. Bye bye.
네, 라플라스 이퀘이션에 대해서 보충 영상을 봤고요. 우리가 이제 라플라스 이퀘이션 갖고 문제를 어떤 식으로 푸는지 한번 조금 예제를 볼게요. 우리가 이제 요 PDE 이퀘이션에서 이제 디퓨전 이퀘이션이죠. 디퓨전 이퀘이션에서 이 스테디 스테이트인 경우로 넘어가면 라플라스 이퀘이션이 되는 거죠. 그러니까 이 라운드 U 오버 라운드 T가 이제 0일 때, 이때 결국에는 라플라시안 이게 0이 되는 이런 상황을 라플라스 이퀘이션이라고 얘기하고, 이거를 우리가 풀 때는 똑같아요. separating variables를 통해서 x랑 y에 대해서 좀 나누어서 생각을 하는 거죠. 이게 나누어서 생각하면 두 개의 ODE가 나오고, 요 아래에 있는 바운더리 컨디션을 갖고서 우리가 적용을 해서 풀면 우선 fx에 대한 솔루션은 이렇게 나오고 g에 대한 솔루션은 뭐 제너럴 솔루션은 이렇게 나오는데 이제 그 y가 0일 때 우리가 요 바운더리 컨디션이죠. 요거 이용하면 요거죠. 요 바운더리 컨디션을 이용하면 an과 bn이 플러스가 an 플러스 bn이 0이라는 걸 우리가 확인할 수 있고 이걸 바탕으로 그 아이젠 펑션이 an으로 이렇게 표현할 수 있는 것을 볼 수가 있어요. 그래서 결국엔 아이젠 펑션은 이 fn과 gn 요거를 곱한 걸로 우리가 표현할 수가 있다라는 거죠. 그래서 다음으로 우리가 풀 건 뭐냐면 이 an 스타 요걸 이제 구하라는 건데 그거를 우리가 주어진 바운더리 컨디션을 통해서 구할 수가 있습니다. 여기서 이제 아이젠 펑션이 이렇게 있고 솔루션은 결국에는 프리 시리즈로 나타나는데 바운더리 컨디션이 우리가 하나가 더 남아 있죠. y가 b일 때 fx라는 어떤 함수로 주어져 있습니다. 얘는 기분 펑션이니까 우리가 결국에는 an 요 bn이라는 애를 그 an 스타라고 포함되어 있는 이 bn을 fx로 표현할 수 있고 결국에는 프리 시리즈 표현되는 이 아이젠 펑션 안에 an이 있고 an이 이제 fx로 우리가 표현되니까 결국에는 제너럴 솔루션 일반해를 구할 수가 있다라는 겁니다. 다음은 2디멘셔널 웨이브 이퀘이션이에요. 요거는 1D보다는 조금 더 복잡한데 요 여러분들이 피지컬 어썸션을 하나 보시길 바라고 결국에는 요 각도를 이루는 y축과 x축의 각도를 이루는 게 스몰 앵글 결국 이제 그 스몰 앰플리튜드 스몰 디플렉션으로 우리가 볼 수가 있고 호리전털 디렉션과 버티컬 디렉션을 각각 구하게 되면 결국 결과적으로 이 힘 방정식에 의해서 이렇게 2디멘셔널 웨이브 이퀘이션이 나타나요. 그러니까 요것만 보게 되면 1디멘셔널 웨이브 이퀘이션인데 이렇게 y까지 포함되는 것이 2디멘셔널입니다. 그래서 라플라시안으로 표현하면 이제 이렇게 표현할 수가 있고요. 그래서 이거를 풀는 방법은 뭐 똑같아요. 결국에는 주어진 식이 2디멘셔널 웨이브 이퀘이션이고 우리가 이제 바운더리 컨디션, 이니셜 컨디션이 이렇게 주어진 거죠. 그러면 세퍼레이팅 베리애블로 통해서 타임 펑션과 앰플리튜드 펑션이 각각 이렇게 나올 수가 있습니다. 그래서 이렇게 나오는데 이때 이 f가 다시 이제 편미분으로 돼 있는 거죠. 그러니까 앰플리튜드 펑션이 x랑 y에 대한 함수이기 때문에 한 번 더 세퍼레이션 베리애블을 합니다. 그래서 이 f라는 함수가 h와 q로 이루어져 있는 것을 우리가 확인할 수가 있어요. 그러니까 즉 크게 세 개의 함수식으로 우리가 풀이한다 라고 보시면 됩니다. 그래서 이 바운더리 컨디션은 여러분들이 한번 쭉 보시길 바랄게요. 그래서 일단 f에 대해서 q랑 h로 표현되니까 바운더리 컨디션 우리가 잘 잡아서 아이젠 펑션 구하고 아이젠 펑션으로 우리가 프리 시리즈 통해서 이 타임 펑션이랑 같이 합쳐서 우리가 풀 수가 있다라는 겁니다. 그래서 프리 코에피션트를 통해서 요 BMN과 BMN 스타는 이니셜 컨디션으로 fxy, gxy 나온 걸로 구하면 됩니다. 서큘러 멤브레인도 있어요. 그래서 이 기본 골자는 이렇게 우리가 2디멘셔널 웨이브 이퀘이션인데 uxx, uyy가 이제 폴라 코디네이트를 이용하게 되면 우리가 아주 식을 이렇게 표현할 수가 있겠죠. 이런 식으로 여기서 이제 주된 어떤 유도 방식은 이렇게 나와 있는데 결과식으로는 R과 세타에 의한 2디멘셔널 웨이브 이퀘이션 폴라 코디네이트로 구할 수가 있습니다. 그래서 요거를 우리가 풀게 되면 베셀 펑션으로 나와요. 우리가 배웠던. 그래서 베셀 펑션의 각각의 모드 넘버에 따른 어떤 웨이브 형태도 우리가 파악할 수가 있습니다. 그래서 오늘 수업은 여기까지 하도록 하고요. 제가 중간중간에 이렇게 유도하는 과정들을 생각했는데 여러분들이 한번 복습하면서 자세히 유도를 한번 해보시길 바랍니다. 경청해 주셔서 감사합니다.